Hello everyone. In our today's session, we'll conduct experiment on evaluation of impulse response of a system. So myself Rishan R, Assistant Professor, Department of Electrical and Electronics Engineering, ATM College of Engineering, Mysuru. As I spoke, we are going to conduct the experiment on the evaluation of impulse response of a system. First, let us understand what is an impulse. So in signal processing, if we talk about impulse response or an impulse response function with respect to a dynamic system, it has its output which is presented with a brief input signal. So that resembles something like this. So if you just observe in this particular case scenario, you can basically see there is a small impulse rise over here. So with respect to any dynamic system, how it is going to perform and how it is going to respond with respect to the external change is what signifies an impulse response. So it has different applications. It can be created by playing a sound, or it can be impulse in random space. It can be something like a short percussive sound, something like if you are starting a pistol and if you are trying to capture that in the signal. It can be a clapboard slate, it can be a balloon popping. All these signals you can basically capture and it can be resembled in the form of a signal. It can be a more sustained sound, even like a sine sweep. Here we can basically see there is an input signal and there is a function which you are basically multiplying. Ultimately you are getting some output response. And its applications can also be viewed in terms of loudspeakers, electronic processing, control systems, acoustic and audio applications, economics, in let's say forecasting with respect to stock exchange. If you want to view different pattern of rise with respect to the let's say there is some inflation, or it may be different money exchange patterns, or it can be different scenario as well. So everywhere you can have different applications of this. So further up, more applications, let's say in civil engineering we have pile integrity testing, floor slabs and wall pavements if you want to record concrete consolidations, cylindrical structures, concrete bridges. All this can be documented as well. In addition, there is high-rise buildings where cladding is required there also. So we are going to speak about the objectives, that is to arrive at a transfer function of a system wherein we'll be speaking about a random representation. We'll take up a random case scenario and we'll try to plot it. So to understand the response of a system for an impulse input. So these are the objectives with respect to experiment number 2. So here I have taken a sample signal where you can basically see the output response with respect to the input parameters. So if I have to solve this, let me try to bring out all the common parameters to one single site. So here I have y of n, I have y of n minus 1 over here, y of n minus 2. I'm bringing to the LHS and all the x parameters to the RHS site. So if I take Z transform on both sides, you can basically see all the n representation, that is in terms of discrete, and converting that into Z representation, that is Z transform. So y of n can be represented as y of z, y of n minus 1 is, n minus 1 here represents Z inverse of y of z, n minus 2 is Z minus 2 into y of z. So likewise on the RHS side with respect to x of n minus 1 and x of n minus 2 with respect to the quotient parameter, that is log 4. So on trying to simplify this further, I'll just take out the common parameter y of z. So all the common parameters on the LHS, all the common parameters on RHS. So if I represent the transfer function in terms of ratio, that is h of z is equal to y of z by x of z. So basically y of z is here is 1 plus 0.5 z inverse plus 0.85 z power minus 2 divided by 1 minus z inverse and z power minus 2. Now I have to simplify this so as to get my coefficient. To do that, I have solved this manually. So here you can basically check out. Previously we have got 1 z minus z inverse z power minus 2 and the parameter 1 plus 0.5 z inverse plus 0.85 z power minus 2. So I'll be considering this parameter over here, that is representative constant 1. So I am considering 1 here in the first case because here I have the representation as 1 as well. So if I product this 1 into 1 is again you're going to get 1. Similarly, if I go for the next parameter, that is z inverse into 1, again you are getting same, z power minus 2 is z power minus 2. Now if I take out the subtraction. Basically, I have to cancel out the parameter in the first instance. There is positive out here, so this is minus. So plus minus, here I'm changing the polarity to plus, plus minus, again it is plus. On simplification, you are getting 1.5 z inverse, that is 0.5 plus 1, 0.85 plus 1, 1.85. In the next instance, you have the constant parameter 1.5, retain that here. So next, again, we are multiplying 1.5 z power minus 1. So 1 into that is 1, again we are getting 1.15 z power minus 1, that is with respect to this parameter I am talking about. So if you are multiplying this with respect to all the subsequent cases, then if you just simplify every particular scenario, after substituting this you are getting 3.35, after substituting this you are getting 4.85. So you can keep on continuing with respect to the solving, and at the end the coefficient what you are getting is 1, 1.5, 3.35, 4.85, and that is your h of n parameters. So this you should be getting as a response with respect to what we just did now. So by power series method as well, the same output can be obtained. So to speak about the program, so here you can basically see it's a very simple program with about 4 lines. So I have a CLC command over here where we can basically clear the screen at the beginning of the program. I'm taking 2 input coefficients section over here, which is represented with the label B, and another one with the representation as label A. So here I have all the x of n parameters which I'll be entering in the output window, that is the command window. I have one more representation y of n minus 1, which I've labeled it to A. You can have any random representation, you don't have to be specifically B or A, anything you can pick out. And how many number of samples that I'm expecting with respect to the current impulse response. So I've considered that as n. So whether we want 2, 3, 4, depending on how much we have solved, it can be infinite number of times. So finally, to solve this entire set of parameters, we have the matrix in terms of h of t, that is basically h comma t, beg your pardon. So where we will be basically trying to solve the impulse z transformation with respect to input coefficient, that is b, a, and the number of samples that we are expecting. And once I'm done with this, I'm going to display the content with respect to my output function that I'm expecting. That is what we just observed in previous slide. And finally, I'm plotting my continuous to discrete representation using my stem function, that is t comma h. So we will be getting the response by entering the coefficient x of n minus 1, x of n minus 2 as 1.5 and 0.85, which we had already observed in the equation, constant parameters. All the y of n minus 1 is 1, minus 1, and minus 1. Now how did we get this? This is, if you carefully observe, this is 1, minus 1, and minus 1. This is y of n parameters, 1, 0.5, 0.85, all these are x of n minus 1 parameters. So if you enter the number of samples as 4, let's say in this particular case, you should be getting your response, and this I just showed you a couple of slides back after solving the representative equation, and we'll be getting the response over here. You can basically check out. Previously we had got this as 1, 1.5, 3.35, 4.85. So this is 1, 1.5, 3.35, and 4.85. So this is with respect to the program is concerned. Now let us just check the result, that is this particular program with respect to your update. So I'll copy this particular program. I'll open Octave 5.1 graphical user interface. I'll go to my editor window and remove the comments which is not required. So I'm saving the file now. Save file. So I'm opening this in the desktop. So let's say this is experiment 2. So already this is in .m extension, so I can save it directly. So I'll execute the program. I'll come out to the output window. So it is 1. You can just check out coefficients that are to be entered, 0.5, 0.85. So 0.5, 0.85. Next, the parameters are y with respect to y coefficient 1, minus 1, minus 1, which I showed you previously. Number of sample is 4. And if you solve, there's a small impulse loading function that it is expecting. So what you have to basically do is use the small command pkg load signal. If this package is not installed in your Octave, you have to enter this command so that you can re-execute this. So after this, once again rerun this command. Now enter the values 1, 0.5, 0.85, next 1, -1, and 4. So here you can basically see the parameters coefficient that we had got, and finally the impulse response with respect to random signals. So this can be documented, or it can be recorded with respect to different applications, and it can be random impulses that can arrive depending on the different sound signals, or it can be random different applications. It can be random spike of impulse that can be plotted and observe what is the result. So this is all with respect to evaluation of impulse response of the system. Thank you.